keep me updated if it remains too small. So I'd like to talk about today about an attack that has been brought forward by Kit Fine against positionalism, which has later been refined by Fraser McBride, and which is against a variant of positionalism, to be more precise, and how he treats polyadic symmetry. And I'd like to first present the two cases, which most of you are familiar with, which are the circle case and the tug of war case by McBride. I'll then present an idea of how to respond to these cases in terms of thinking about relations as being composed of other relations which I call the concatenation of relations. And I'll then try to give an account of how to account for the completions of polyadic cases of the kinds we'll be looking at now. So I'll start first with the ontology, or the positionalism in general, and how which is my notation for it. So the ontology of relations, according to the positionalist, is such that we have positions. Like in the binary case, we have an alpha and a beta position, for instance. And then how do we understand the exemplification of relations? Well, it's through assignments of objects to positions. Can you see my cursor, by the way? I don't see anybody of you. Can you see my cursor when I use it? Okay, perfect. Now I see you all. So it's assignments to positions. And for instance, in a binary case, we would then say that we have dual assignments of an object X to the alpha position and an object Y to the beta position, which would give us the relational state, or the completion of this relation XY. And well, the good thing about this is, of course, that we can account for differential application for non-symmetric relations. So if we assign Y to the alpha instead of to beta and X to beta, then we would get the relational state YX. So there are basically two variants of positionalism, or two which I find important. The first one holds that an n-ary relation has n distinct positions. So a binary relation would always have two positions. But while this is good for an account of, or for accounting for the differential application of non-symmetric relations, we run into trouble with regard to symmetric ones, because when we have two distinct positions, there are always two ways for two objects to be assigned to these positions. So this is what I call, or what some authors call, the symmetric state overabundance. For instance, if you have the next relation and you have two next positions, we end up getting two next relational states in the end, where we expect only one. So this is a basic problem we will find over and over again, as I'll show you throughout. So one response to this is to say that, well, symmetric relations have only one position, and this position can be repeated, or as some authors put it, that we can multiply, that an assignment can be multiplied, or there can be multiple assignments to the same position. So whenever I note this, I don't want to be bound to a particular ontology underlying what it exactly means, or what positions exactly are, but you can just choose the one you prefer. So either it's a repetition of positions, or it's a multiple assignments. It's multiple assignments to one the same position. So the advantage is that we, of course, get the correct number of states for binary relations, because the extended positionalist holds that symmetric relations have these repeated positions, whereas non-symmetric ones have distinct positions. The trouble is this extended version of positionalism, which I call just positionalism, fails with polyadic symmetry. And this is what the following cases are all about. The first one is by, oh, sorry, it's too big, I guess, at least on my screen. The first relation is the relation R, A, B, C, D of being in a circle in that order. You all know it, and it's so troublesome, and it's amazing that it's just in a footnote. And how do we account for this when we are positionalists? Well, the suggestion is that it's the same position multiple times over. And how do we account for the completion of that relation? Well, we plug in the 4 objects, A, B, C, and D. And we might start here. It's a spatial. I've chosen the spatial being in a circle for illustrative purposes here. So if we start plugging in A, B, C, D, starting on the top, what we get is the completion of the relation we want. But we could also start here, A, B, C, D, or start there, A, B, C, D. And that's what renders it symmetric. Because if you look at the objects, it's the same assignment for all objects. But the trouble is, if we look at a distinct state of affairs, R, namely RA CBD, and then how do we account for its completion? Well, we plug in each object into the positions. Yeah, we assign them to the positions. R CBD, or we start here, R CBD. We can go around. It's symmetric. It doesn't matter because it's just one position. So we end up getting RACBD, but what we cannot is differentiate it from RABCD. Because if you look at each object, what's its assignment to a position is, it's just the same assignment to the alpha position. Because we have one, there's no basis for distinguishing these two states, which we assume to be distinct. So that's the first case. And since the positionalists cannot distinguish between the two relational states and how to complete them with this buildup of positions, positionalism fails, at least this variant, right? So the second case that McBride asks us to explain, this the second relation he asks us to explain, does not contain anything non-symmetric, but only symmetry. And the relation is 4 people playing tug of war in 2 teams of 2. So it's the person AB against CD, but first it's 4 people, first and foremost, 4 people playing tug of war. And well, if we ask the positionalist, what's your buildup of positions to account for a state of these 4 people playing tug of war against each other? Well, here's the first suggestion. Of course, it's symmetric. It's everyone playing tug of war with every other. So it's a symmetric quaternary relation. And we have one position, and we plug in the people, and it doesn't matter where we plug them in. And well, that's the Viking way to play tug of war. And well, what's good about this is, of course, we plug them in, and we have a symmetric. We get a symmetric. We have a symmetric situation here because it's just one state that we get out of it, because each object is assigned to one of the same position. But of course, we want teams, and we cannot get teams from this. So here's the second suggestion the positionalist gives us. We throw away the first one, the first position buildup, and this is the one we should be looking at now instead. Then we have 2 positions, and each position for each team, right? So we have the gamma position twice over, and we plug in A and B, and we have the delta position, and we plug in C and D. And now we are able to say that, well, there are 2 teams of 2 people playing against each other. Well, are we really, what are we doing here? Do we have a symmetry? We don't have the symmetry anymore of playing tug of war with any player that we had with the first build-up. So that's what I take to be the first problem about this, because we're now saying that it's 2 teams of 2 playing against each other. But there's a second problem, and that is that we have a polyadic instance this time of this symmetrical state overabundance. Why is that? Well, what we want is a state of 2 teams of 2 playing against each other. And this is what we get when we plug in A and B in the first position in the gamma position, and C and D in the delta position. But we get again a state of two teams of two players playing against each other when we flip them and we plug in A and B into the delta position and C and D into the gamma position. So we get two states of two teams of two playing against each other where we expect only one. So this is the second problem. Two problems in this case. And last positionalism fails because the first build-up of position gave us the wrong number of states. And the second one, this one, it's the same. So it's a wrong number of relational states. So the consequences are of these cases. Well, first, the simple positionalism fails. Simple being the one that has n distinct positions for an n-ary relation. And this extended version fails because of the cases just presented to you, where the positionalist fails as well to give us the right positional buildups, to account and explain the correct number of relational states that we want. So that's what I take the main problem for a positionalist, that he cannot deliver the right position build-ups. So either position build-ups, either of the position build-ups he presents to us does not get us the right state identity. So that's what I take to be the main, or that what seems to be the main problem. And we have this further problem of the polyadic instance of symmetric state overabundance. So my analysis is a little bit different. So what it looked like, the positionalist fails with either, it looks like he fails with either of the options of position buildups he presents us. What I think is that he fails instead with the either of the buildups. He failed with the either, because I think instead we should look at these cases as completions of arrangements of relations and not just of flat relations. The way I'd like to look at these cases is to see them as cases of relations that are composed of or what one could call flat relations, so that we get complex relations which are not flat, but which are more or less relations piled or stacked upon another, and of which we can then say that they are partially symmetric and partially non-symmetric. And of course, when I first say this, it's absolutely not clear how we could complete them and how we could systematically explain their completion. But what I want to demonstrate is that the positionalist provides the layers of all the flat relations, that we need some minor additions, only minor additions, to account for the complexes. So the basic approach, basically the approach of the positionalist is that we have complex positions that are endowed with positions and in addition with superpositions, and that we will account or should account for their completion by assignments to superpositions in addition to assignments to positions, as we know it from the positionalist. And well, the basic idea is the composition of relations. And how does it work to compose complex relations? And when I say complex relations, I mean relations that are complex before they are even completed. So we are in a pre-completion state. There are no objects involved yet. So how I think about them is not as mere sums of relation, but instead as a sort of concatenation of overlapping layers of relations. And one might figuratively look at them like this, but of course it's not clear what the overlap is when I just draw them. Is it big enough, by the way? Can you see it? Okay, it's perfect. So I found somewhat of a precursor of what I had in mind in the relation algebra, or the calculus of relations, that was invented by De Morgan and Peirce, and later which has later been developed by Tarski. And it's a mathematical theory, of course. But what we find there is how to make a new relation from two old relations. And what's crucial about it, or what I find so interesting about it, is that it is defined with the joint element. So here's how one would define the Peircean relation composition. You get xz, just in case there exists a y, such that xy is an R and yz is an S. A quick example what that means, or how to understand it, is if we have the relation R of being the son of and the relation S of being the brother of, then the relative product of R and S is the relation nephew of. And this is how one might look at it. What's going on here? We have this link element, and we get a new binary relation. And that's, of course, the first adjustment, the first small adjustment I want to make in order to get an answer to our polyadic problems. I think we should look at relation concatenation, which is very similar to the one we've just seen, the Peircean composition of relations. But instead of just requiring a link element, we're now integrating it. So we get a polyadic x, y, z, just in case there exists a y, such that x, y is an R and y, z is an S. And this is how one might look at this. So the product is not binary, but we're increasing the arity by including the link element. And here are a few examples. I pick out only one, only the first. Think about the telephone chain as phone calls were worked in the past, where you called the central office and then the central office connected you to a callee. So thinking about these three, the caller, the central office or the switch, and the callee, all three, and the state that they are in when a phone call is happening. That's an example of two concatenated relations. But crucially is the second modification I would want to make. Of course, we don't want order and we don't want a mathematical theory, but instead we want to understand relation through positions and their assignments. We want something intentional going on, and we don't want converses. That's why we're going for the positionalists in the first place, of course. But what then is the overlap? What then is the overlap? This link element that we assumed in the Peircean composition case. Here are two relations, two binary relations, and we want some overlap. Yeah, but what is it? What is this overlap of two positions? The best way, I think, to understand this is by looking at an actual state of affairs. Let's say this one. We have three objects, A, B, and C. And we have two relations, the relation of A being brighter than B and B being next to C. And that's something quite ordinary. But what's very interesting about this, if you ask me, is what's going on here with regard to B. B is playing two roles. It's less bright than A, and it's next to C. And by that, what's happening is that two relations are concatenated. They're snapped together. B is sort of a latch. And that's how I think about relation concatenation. Because if you flip the perspective, to get a state where two relations are concatenated or are snapped together or are whatever, are like linked together as they are in this state, we would have to say that we want an arrangement with layers of relations. And what's going on is that the object that is assigned to one position of the one relation has to be the same object that's assigned to the position of this other relation. And I think about these two positions, this complex of these two positions, which are assigned to by one and the same object as a superposition that objects can be assigned to. So an assignment to a superposition is what's going on when two positions are assigned to by one and the same object. And that's basically it. That's basically what a superposition is. It's no new fancy ontology. It's the minor addition of identity of the assignee objects of two distinct relations. And by that, I hope it's enough to glue relations together. And that's the basic principle that I think is enough to construe a whole lot of complex relations. So to give you an example how the assignment or the completion of such relation works, it's similarly to the positionalist view of what makes the difference. It makes the difference what position an object is assigned to. And here it makes a difference in a superpositionalist complex view of looking at arrangements of relations. It makes a difference if an object is assigned to a position or if it is assigned to a superposition. So that would be distinct, of course. If you look at the state of a murder going on, of somebody shooting at, in this case, A is shooting at B while B is next to C. It makes, of course, a difference if you're the person just standing to B. It doesn't make a difference for the completion of next to, which position you're in, but it makes a difference if you're also assigned to the being shot at position of this other relation. So it makes a difference if you're just assigned to a position or to a superposition. And so these are two distinct states of affairs that we get by assigning an object to position or to superposition. And I would like to generalize this a bit. So the basic principle is having the identical object being assigned to distinct positions to count for an assignment to superposition. And we can build a lot of stuff with it. Of course, this, what looks a bit like a Tetris piece, is just two binary relations that have one superposition. And already here, we can draw all the distinctions that the positionalist does with regard to the layers, to each layer. So we can have two binary relations where one is non-symmetric and one is symmetric, or we can have two binary relations that are both non-symmetric or that are both symmetric. But there are a lot of arrangements based on this superpositionalist principle. We can have, of course, polyadic input relations concatenated together. Both could be polyadic or only one. What we can also have is multiple superpositions. Let's look at the second one first, maybe. Think about the relation being the son of, where the son is assigned to son of position and the father is assigned to the father position. And where it's also the case that the murderer is the son and the one being murdered is the father. And what we get is the patricide relation, and it turns out to be a complex relation, instead of being just a flat relation. And here in this example, we also have two superpositions, but this would be described as wholly symmetric, because in the case of the patricide relation, of course, it matters if you are if the son who murders who, or who is in which superposition. It makes up for a distinct state of affairs. But in this case, if we have the same superposition twice over, doesn't matter where each object is assigned to, would end up in the same state. So that's the same principle that we allowed or that we had in the positionalist case, where an assignment to the same position by the same objects results or completes the relation as the same state, as one and the same state of affairs. Another arrangement would be this, for instance, where we have multiple input relations, more than two, concatenated like that. Or we could have a greater depth for either superposition. What this just means is, well, it has to be the same object that is assigned to each of these positions. And we can have superpositions with this different depths, yeah, within the same complex or the same arrangement of relations. So what's important about the superpositionalism? First, which positions and which superpositions you have decides which arrangement we're looking at, or to put it another way, what arrangement you have depends on which positions and superpositions it is equipped with, this complex. But it's quite a different story which completions of arrangements you get. And how is this explained? Well, by assignments of objects to these positions and superpositions. Well, now let's try to apply it to the two cases we were looking at in the beginning, and how I think this might help. First, we start with the layer of being in a circle. We want it to be symmetric, so we have the same position 4 times over, and yeah, we assign the 4 objects to it. What we do now is we add a layer of absolute positions. It's the first attempt, which is already quite nice, I would say. We have now 4 superpositions instead of having just this one layer. And what we're now saying is that A is assigned to this first column, which is the superposition, B to the second, C to the third, and D to the fourth. And we get the completion R, A, B, C, D. What this is a layer that is non-symmetric, and this is a layer that is symmetric. So about the completion of R, A, B, C, D, we can say that it is symmetric because it is partially symmetric. What that means is it has a layer for which it makes no difference where we plug in any of the objects. But since A, for instance, is not just assigned to the position of this layer, but instead we're describing this arrangement and its completion, A is assigned to a superposition that has these 2 layers, or these 2 positions out of each layer. So we can now distinguish A CBD from A BCD, or R A CBD from the first one, because we can now say that B and C swap their assignments with regard to the superpositions. It wouldn't make a difference if we have just this layer, just the layer of being in a circle. But it makes a difference if we have these superpositions. So if you compare R A B C D and R A C B D, we can say they're both symmetric because they are partially symmetric. But we can now draw a distinction. We can now differentiate them in terms of the position setup, because they are assigned, the objects are the same set of objects is assigned to distinct superpositions in either case. I come back to this circle because I have a small adjustment to make. But first, let's look at the tug of war. How does tug of war work? Well, we started in the beginning with the build-up or the setup of positions that allows us to say each player plays tug of war with each other player. And this time we're not throwing it away, but instead we are piling it up with the second candidate layer, which allowed us to have 2 different teams. And what we're now doing is we're assigning objects to these superpositions. So one person is playing tug of war and is in team 1, which would be A and C in this one. Sorry, A and B into the first superposition, and C and D into the second superposition. And what this allows us is to say that, well, we have 2 teams of 2, which are all playing tug of war. Each of them is playing tug of war with every other. So that's the first thing that's good about it. We can account for both teams and tug of war. But of course, there's this second problem of symmetric state overabundance that we found already in the binary case. We found it in the flat polyadic case. And now we have these 4 superpositions. And we have it again because, of course, we could plug in A and B into this position, and C and D into this position to get us the state we want. But we expect this to be the same state as if we would have plugged in C and D into the first position and A and B into the second. So how do we deal with this? Well, my answer is this. What's going on here? Well, we have the symmetric tug-of-war layer, and we're now able to have the team layer twice over. What is this move? Well, I think it's the same move that the positionalist makes when he says how to explain symmetry. Well, by assignments of objects to the same position multiple times over. And in this case, we're saying, well, how to account for symmetry in these complex relations or in these complex arrangements of relations. Well, we can have relations multiple times over. And what matters now is, of course, what these relations are, what objects are assigned to these relations, this time as couples if they're binary. So it makes a difference if we plug in AB into one team layer and CD into this one, but it doesn't matter where we plug in AB, into the first team binary relation or into the second one, which is the same. It's just the same, and it's symmetric. But it would be a distinct state, of course, if we assign another couple to the binary relations. So if we plugged in A and C into this binary relation, of course, we would end up getting a different state of affairs. But if we plug in A and B into the binary relation and C and D into this, it doesn't matter where we plug them in because it's just the same relation. It's the same move that we did intra-relationally. We're now doing it inter-relationally, like within these complex arrangements of relations. And well, if you think that this is not enough, if this doesn't sort of account for the particular state we had in mind when we first introduced it, well, to show the versatility of this superpositionalist approach, we could just add another layer. We could just say, well, if we had only the first 2 layers, the tug-of-war layer and the teams layers, if you want, then this is just a co-op game. It's just 2 teams of 2 playing tug-of-war. But what we want is, we want factions in addition to that. And then we could say that each person that's in one of the teams is pulling left, for instance. And well, everyone who's assigned to these positions, to the factions positions, what makes the difference? So you have teams playing against each other. Maybe it wasn't captured in this, but you could add even more. You could add even say that the two people standing in front have to be the tallest people, or they have to be the same size, or that the person standing in the back has to be female, or stuff like this. You can model it all, and you can account for the right numbers of states. And now if you think back, what we demanded of the positionalist in the beginning, we asked him to come up with only the distinction of positions being the same or being distinct. But arrangements of relations can be so much more complicated. And the way I think about them is just as relations, which are not only polyadic, but which are complex. Complex meaning, well, they have these layers. And we can now go back to the circle case and try to get us something that's more of a relative positioning, if you want so. So we could say about the 4 objects being in a circle that A is next to B, for instance. This could also be, we could also model this as a non-symmetric being clockwise or being later than A, or being, yeah, anything non-symmetric. But this suffices to make the point, hopefully. So we could say that A is next to B, and then just add more binary layers, which we can concatenate, so that we have all of them being in a circle. And in addition, we have these binary segments, which gives us this one in the end. We now have the repeated occurrence of the next to relation. We can say that, you can say that A is next to B, B is next to C, C is next to D, and D is next to A. And they can move sort of like in a real ring of roses, as long as the couples, the assignments to the binary segments remain the same, right? So if we swapped C with B, for instance, we would get the binary couple AC assigned to one of these binary relations, which would give us a distinct state of affairs. So it matters which couples are assigned to the to the relations. So I think that's the way I would model what we were after when we said we want 4 objects to be in a circle in that order. One might think, well, maybe we don't even need this layer. Maybe this is just the spatial layer of being in the circle, like when you have points anywhere in the circle. We can just delete it and have only the first two, the first 2 rows of relations, if you want. And maybe that's what we were after when we said we want the cyclic relations of the 4 objects being in a circle. And in a sense, it captures this as well. So we just have to be clear what state identities we're after. And I think with the help of this framework, we can account for their completions. And what's the time? Is it 10 minutes left? Is that correct?
Let's say 7 minutes.
7 minutes, because I'm almost done. I have just 2. Oh, let's start with 2 objections. Well, first one might say no complex is the completion of 2 distinct relations, and of course, what we've done here is to show how complexes or how completions can be the completions of complexes that are construed by a lot of relations. But of course, the complexes we've been looking at were complexes where relations are parts. And what this uniqueness principle is against is, of course, converse relations. And converse relations are not parts, or I don't know of any account that sees the 2 converses as parts of a bigger relation. So it's really that we want to say no complex is the completion of 2 distinct maximal relations. We want to say that, of course, we cannot just have a completely different build-up of relations that gives us the same state of affairs. We cannot just exchange it for another, as would be the case with the converse relations, where you have greater than giving you the same state as being less than, A being greater than giving you the same state as B being less than A. And here, I don't want to say that we can just replace any of the relations that are piled up, but we need them all. We really need them all. So this is the reply. Another maybe objection would be to say, well, it makes no sense to identify positions among relations. So positions are interrelationally non-identifiable. And one reason for holding this could be, well, if positions could be identified, interrelationally, then there is this possibility of having converse relations within the positionalist realm. And we want to block that, and that could be a motivation for holding such a view. What I would reply to this would be to say, well, I don't see how converse relations could come up in the positionalist framework in the first place. So I don't see why we should block them, because it makes a lot of sense to compare positions interrelationally. And I think I need it for my account, at least for the repetition of positions within these complexes as I've presented it. And well, maybe a minor extension that I have in mind. Why not think about unary relations, also known as properties, in terms of positions, as just having one position? Then we can make a lot of sense of structural universals, because we can sort of type restrict the atoms. And the way I've been looking at structural universals is, of course, by focusing these bonding relations. And they are much more complicated, I would say, than talking just about the atoms and about their nature, because they are so interconnected and interrelated. So with the minor addition of having monadic layers, I think we can model structural universals. And the second use case would be maybe to reduce non-symmetry. So imagine the binary non-symmetry. What if we said, well, it's nothing about the nature of non-symmetry of a binary relation, that it's non-symmetrical, but instead that every non-symmetric relation is instead a complex of a symmetric relation and a disbalanced distribution of layers, in this case of a monadic property, like being the sibling of and being male. Maybe that's the brother of relation, being the brother of relation, or cases like these. I have a few other extensions, but let me conclude that I think what we really need is an account of complex relational arrangements. And this is not just for the positionalist, but I try to show that the positionalist is a really good view to model them and to account for their completions. So I think positionalism provides the basis for explaining the problematic cases we were looking at, with some additions from the superpositionalist. Yeah, that's it.
Thank you, Claudius.